polar equations as well. I shouldn't use the word functions for these, but parametric and polar equations. There will be some prereq days built in. I would hope you remember this stuff from PreCalc, but I also know it's some stuff that's just you need a reminder of before you do the calculus with it. So you will notice you're looking at the calendar. Today we are going to focus on prereqs with the parametrics, and then we'll basically have 3 days of doing calculus with parametric functions. And then we will end this week with another prereq day, and that's going to be with polar functions and polar equations and polar graphs. And then we have 2 days with calculus and polar equations. Do notice this unit, there is no quiz. There's just going to be a test. So we will just have one assessment for the entire unit. Even though it is a short unit, this topic or these topics are going to end up being between 17 and 18% of the BC exam that you have, which is a pretty high percent. So you might be wondering why I'm not spending more time on these topics. Short answer is we just don't really have the time. But also you will notice, like, once we start reviewing these, a lot of the calculus we do with these problems is basically just applying a lot of the stuff that we did first semester. So we really will be kind of reviewing a lot. Instead of dealing with like finding the derivative of y equals, we might have like find the derivative of r equals or find the derivative of the x and the y. And so there really isn't going to be difficult calculus. It's just making sure we remember how to kind of work with these types of graphs. So what I wanted to focus on today is going to be the parametric stuff. And I just want to kind of focus on the stuff that we did last year. Some of these problems I actually have in these notes, I just stole from the notes we did last year. And the things that we want to mainly do when we're talking about parametric equations, like a general understanding of them, we want to be able to graph them both by hand and with the calculator, but also be able to kind of reason our way through like what the graphs could look like without having to graph them. And we'll talk about what that means. And then also sometimes these problems are just easier to do as a regular equation. So going and reminding ourselves how we can eliminate the parameter and write it as one that we're more traditionally used to. So to define some things, I did want to go ahead and define again for us what a parametric equation is. A parametric equation is basically going to be an equation that gives the coordinates of points on a curve as separate functions of a parameter, and we often use the variable t as our parameter equation. There's different ways that we can write these. Sometimes they might just say, hey, here's the x coordinates equation and here is the y coordinates equation. Sometimes it'll be written more like a point, like x of t comma y of t. Sometimes we'll also write these as vectors, but the interpretation is not the same. We still have the x equation and the y equation. So even when we are thinking about it in vector notation, like they are going to be essentially the same. And so we'll have the x to t, which is going to be an equation for the x's, the y of t, which is an equation for the y's. They work together and create the curve. Oftentimes that parameter of t we can think of as time. And we often see these types of problems for PVA problems with position, velocity, and acceleration. So often and truly, it will represent time. But even when it's not one of those problems, you can think of it as time. As time changes, this is what x is doing. As time changes, this is what y is doing. So first thing, graphing them by hand. Here's a representation of a parametric. We have x comma y is equal to 3t comma 9t squared plus t, where basically the equation for the x is 3t and the equation for the y is that 9t squared plus t. There's different things that you want to be careful with and things that are important when you're doing parametric equations. Obviously, you have the shape, like what does that graph looks like? And then you also will have something that's different from a regular equation, the orientation, which is basically the direction. So the order of the points that show up will matter. So if I have these different parameters, again, I kind of just chose these at random, -1, 0, 1, 2, and 1 and 2. Sometimes there might be a domain restriction on t, like maybe t is only between 0 and 2 pi, or maybe t is only greater than or equal to 0, or maybe t is all real numbers. This one I just kind of chose 4 values for it. We can plug that in, so I have like for the x's, that's 3t. So 3 times -1, 3 times 0, 3 times 1, 3 times 2. And I can do the same thing for the y's. 9 plus -1, that's going to give you 8. When t is 0, the y is 0. When t is 1, the y is 10. And when t is 2, we see that y is, that's going to be 9 times 2 squared plus 2, which is 38. So I'm plotting those. Again, that was just kind of making like a t-chart. I can kind of plot those pretty efficiently. -3, 8, 0, 0, 3, 10, and then 6, 38. This is a quadratic, but what's important is we'll also show like some arrows on it to show the orientation or the direction of this graph. So with a parametric equation, not only is this a quadratic, it is a quadratic moving to the right. So that's how you would graph it by hand. Also want to know how we can kind of graph it in the calculator. I've shared with you, I know we did this last year, but I have shared with you kind of the instructions of how you do this in the calculator. I'm going to switch screens in a second. I'm on my Surface, but my Dell's the one that has the calculator program on it. You do change the mode, and we will be kind of changing the mode fairly frequently this week between parametric, function, and then eventually polar. When you change it to parametric, the button that gives you your x's will now give you t's. And your y equals will now have like an x equation and a y equation. I do recommend changing the cursor for our graphs to be the one that has the tadpole. And again, I'll show you how to do that on the updated calculators. That's only because the direction is important. So sometimes it's nice to have like a little ball kind of tracing so you can easily see the direction. And then the other thing that's important to remind ourselves is like the t-step. That's basically tells the calculator like how often to plug in a t-value. The smaller that t-step, the slower it's going to graph, which can sometimes help you if it goes up too fast. It can help you kind of see the direction. So if I'm graphing this one, bear with me 1 second while I switch screens. I'm going to go into my calculator and go ahead and change the mode first. That's always the first thing you want to do. So I hit mode, and I'm going to change this into parametric mode. And then second quit. Y equals will now give me like a fresh kind of window to look at. Looking at the equations that we are graphing, we had the one that we just did, x was 3t. I'll use the X button for that. And then the Y is 9t squared plus t. And I already changed mine from third period, but if I'm up on this line with the X's and go to the left, if you have an older calculator, you're just going to keep hitting enter over and over and over again until you see the little tadpole. This is one of the newer ones, so I'm going to select it. You can kind of see there's different options to choose. To me, for parametric and polar, the tadpole is going to be the best one because it will allow you to see the shapes that you're kind of dealing with. So that's the one I'm going to select. And then I'm going to go ahead and adjust the window. Like, I already know what this graph looks like. So I am going to let my Tmin and Tmax, yours might be from 0 to like 2 pi. I want some negatives and positives. So from going from -10 to 10 is typically good enough. My t-step 0.5 is often good. This is on my computer, so it graphs it pretty fast. So I'm actually going to do 0.05 to slow it down a little bit. And my y maxes, I changed from -10 to 40, just because I knew that the highest y value I had was like a 38. But now graphing it, I can see it's coming in from the left and then finishing out that quadratic shape. Again, having that cursor is kind of nice, especially if it comes through a little bit faster. It will kind of catch your eye so you know the direction of it. And again, the direction is important. That is a component of the equation. Yes, Seth?
So how do you determine the orientation without a calculator?
We'll get there.
Okay.
I promise. So go ahead for me, and I do just want you to have practice using your calculator. So let me go ahead and switch my screens back over. On the next slide, if you're following along in OneNote, I have 3 graphs. And again, I just want you to get familiar with your calculator. Go ahead and graph those 3 for me. Granted, we already did that first one, but I want you to graph those 3. Pay attention to, of course, the shape and the orientation of it. And then we'll talk about how we can kind of analyze these more algebraically without the calculator and graphing. But go ahead and take a few minutes, again, to kind of familiarize yourself with your calculator. I'm going to be doing the same thing. You'll see me drawing stuff on here, but then we'll kind of go back and talk about each of them. And again, what's important is making sure you have the shape and then also kind of putting the arrows on the graph to show that you do have the different orientations. So go ahead and take some time doing that, and we'll resume in, won't take you too long, about 2 to 3 minutes. So looking at these 3 graphs, and again, I mainly just want to make sure we know how to use like our calculator for these. Whenever you're done with parametric mode, make sure you always go back and click the mode button and put it back into function mode. I chose these 3, and actually these are the same 3 we did last year, but these 3 all had the same shaped graph. These are all forming a quadratic shape, but the orientation for them is different. This first one is a quadratic where you're moving from left to right, and you can kind of see the arrows I have on there for that. The second one is the exact same quadratic, but it's moving from the right side of the graph to the left side of the graph. The last one is kind of unique. It is still a quadratic, so like you can kind of imagine it's still that same exact quadratic shape. I'm going to zoom in on what I did. but it's stuck between two values. And it kind of, if you looked at the cursor, it moved from left to right, and kind of just repeated for a certain amount of time. But it still was a quadratic. And you can kind of see where this is headed and where this might be related to calculus, especially in the context of PVA. Now we can talk about particles instead of moving like horizontally and vertically, like particles can really just move in whatever shape we want them to when we define it parametrically. So that's how we would use the calculator. We could do the same thing if we were graphing it by hand. But one thing that is important, and I think it's really important when we start doing the calculus, is being able to figure out, kind of going back to what Seth asked, like what the shape is without having to graph it, and then also figuring out the movement of it without having to graph it, because ultimately that is going to save time. And we might be doing a problem like this without a calculus. We want like an efficient way to figure out the shape and the orientation. So how do we do that? The easiest thing to do is to talk about how we can get just to the shape of it. And that's what we're going to do if we're going to convert it from parametric form to rectangular form. So I took that first equation, the 3t comma 9t squared plus t. And if I want to convert this from parametric form, which it's currently in, into rectangular form, that is sometimes also called Cartesian form. That will tell us the shape. So we'll have the same shape. It's going to be more familiar to us. But Cartesian has no orientation. For example, if I say graph y equals x squared, that is a quadratic without any movement to it. So we will lose the movement. So we will have to kind of talk about how we can get that movement back. But let's just talk about eliminating the parameter right now. In simplest terms, you're going to have to do some sort of substitution. And you basically want to eliminate that parameter of t and just be left with x's and y's. Sometimes you solve for t, sometimes you solve for a trig expression, but you're doing some sort of substitution. Most of them, especially the ones that are like polynomials, we're just going to solve it for t. So if this is my x equation, x is equal to 3t, pretty easy to see that then t would be equal to x over 3. And then we can just kind of substitute that in. Well, what is y? Y is equal to 9t squared plus t. T is x over 3, so I can just plug it in. We have eliminated the parameter, but we often want to simplify that. So I have y is equal to 9 times x squared over 9 plus x cubed. Our y is equal to x squared plus 1/3 of x. What this tells us is that this original parametric equation has the exact same shape as y is equal to x squared plus 1/3 of x, which will be a lot easier to graph, like set it equal to 0, find the x-intercepts, we know it's a quadratic, and it's a lot more familiar. What is missing is if there's going to be any restrictions, like is it the full parabola, is it part of the parabola, or do we have any type of direction to it? And we can actually determine any restrictions we have typically by just looking at the x equation. So what I mean by that, we have x is equal to 3t. Well, looking at this, there are no restrictions on t, meaning you could plug in any number into t and you would be able to find x. Like there's not like a square root there or a trig, like any value of t is going to work. Since all values for t work, I know that in this rectangular form of the equation, its domain is going to be from negative infinity to positive infinity. It always works, it's always good for it. We have the entire quadratic. I can also use this statement to figure out whether it's moving to the left or to the right. And that parameter, again, is representing time. Time moves in like a positive motion. So how I kind of think about this, whether I write it down or I just think about it in my head, as t increases, x, and then you want to think about what x is going to do, because again, x is going to talk about the left or right motion. So as t increases, well, x is 3 times t. T is increasing, so 3 times t is increasing. So what is x going to do? Well, x would also increase. So as t increases, x is increasing. To put this in other words, as time passes, that's the same thing as thinking about as t increases. The points are the curve move right because x is increasing, so points are moving to the right. So kind of putting all that information together, I knew I have this quadratic shape. There's no restrictions, so I knew it was the full quadratic. As t increased, x increased, so I knew it had to be a quadratic moving in the direction from the left to the right. Questions on that one? All right, let's do the same thing. So when we graph the calculator, I know we did those three. Let's just analyze them, say we hadn't done it in the calculator. So I have x comma y is equal to negative t comma t squared minus 1/3. First step, we want to get the basic shape. How do we get the basic shape? We want to eliminate the parameter. Well, x is equal to negative t, and I often use the x one. Then what does that mean? That means that t is equal to negative x. So then always going to do some substitution. The y equation is t squared minus 1/3 of t. What was t? Negative x. So y is equal to x squared plus 1/3 of x, which is, as expected, the same thing we got for that previous problem, because again, they all had the same shape. How do we know if it's going to be the full parabola? Look again at the x equation. X is negative t. There's no restrictions that we can place on that. You can plug in any value for t. So I know that the domain of my graph is going to include all real numbers. So we do have the full parabola. To think about the movement of it, we want to think about what's happening as time passes. So we think to ourselves, well, as t increases, x is going to do something. Well, x is negative t. So as t is getting bigger and bigger, x is going to end up doing what? X is going to get bigger and bigger, but in the negatives. So x is decreasing. To translate that into some other terms, as time passes, we are moving to the left since x is decreasing. So I knew I had a quadratic. I knew the domain was all real numbers, so it was a full quadratic. As t got bigger, x got smaller, so I knew that that parabola will be moving from right to left. Questions on that one? All right, last one. I chose this one. We do often see a lot of trig with parametric equations. When we have trig, I often, when I do my substitution, don't solve for t. I often just solve for a trig expression instead. What do I mean by that? We know that x is equal to the cosine of t, and y already has some cosines in it. So I can do my substitutions directly there. Y is equal to cosine squared plus 1/3 of cosine. Well, what is cosine equal to? Cosine is equal to x. So again, we do get the same shape, which is what we expected. It was a quadratic. So again, the rectangular version of the equation tells us the shape of the graph, but it doesn't tell us the orientation or any restrictions on the graph. We can use the x equation to help us determine any of the restrictions. So what is the x equation? X is equal to the cosine of t. So let's think about the restrictions first. Well, if x is cosine, think to yourself, what does the graph of cosine look like? Cosine looks like this. It definitely does have some restrictions. What is the cosine of t always going to be stuck between? It's always between -1 and +1. It can't go outside those boundaries. Well, if x is cosine, then if cosine is stuck between -1 and 1, then x is also stuck between -1 and 1. And that ends up being the domain of this graph, which is why when we graphed it, we saw it was a quadratic, but it only happened between -1 and 1. If you remember, this graph also kind of bounced between those values. It kind of oscillated. You can kind of think about why that might make sense. Thinking about that parameter, as t increases, x is going to do something, and we want to think about what x is doing. Well, x is equal to the cosine of t. What is the cosine doing as t increases? Is going up and down, up and down. Mathematically, we're going to call that oscillating. So as t increases, x oscillates, or basically as time passes, the graph oscillates, which means it's basically going to move back and forth. Which is why without the calculator, I knew this graph was stuck between -1 and 1. And it kind of went back and forth, over and over again because of the shape of the graph and because of the way that trig played a role in its shape. Questions on that one? All right, so I just have one more example I wanted to do, and that will put us at the end of class. Just one more kind of trig example. Again, we haven't done any of the calculus yet, but having a kind of firm understanding of these graphs will help make the calculus a little bit easier. The last and final way you should remember how to get rid of any parameters is sometimes you have to use a trig identity. And for us, the only trig identity that we really need to know is the Pythagorean identities, which of course everyone knows the original one. And then we can get to the other two by either dividing everything by sine or dividing everything by cosine. So we have sine squared plus cosine squared is equal to 1. Our 1 plus cotangent squared is equal to, and this is me dividing everything by sine, cosecant, and I'm just using t's here since it's a parametric one. The other one, divide everything by cosine, so I have tangent squared plus 1 is equal to secant squared. And again, why are those important? Sometimes it's hard to solve for t, but if you notice, both x and y have maybe a sine and cosine in them, or maybe they both have a cotangent and cosecant, that is a relationship that's true and a relationship we can use. So again, looking at this one, we have x is equal to 3 plus the sine of t, and y is equal to 1 plus 2 cosine of t. This one does have some restrictions on t provided to us. It says t is an element from 0 to 2 pi. That little e symbol just means like an element, like it's basically like t is basically between 0 and 2 pi, which makes sense. This is going to be something probably circular. So it could be like a circle, it could be an ellipse, it could even be a hyperbola, which is, we know, related to it through a conic section. So this would be a harder one to solve for t, to plug it in and solve for. But we do know relationships between sine and cosine. So if I solve for sine and cosine, I can build that relationship. So for the x's, we'll get sine of t is equal to x minus 3. And then for the y, it's going to be the cosine is equal to y minus 1 divided by 2. How is that useful? We know this is always true. sine squared plus cosine squared is equal to 1. And we can just plug those equations in. So I'm going to have x minus 3 squared plus y minus 1 over 2. All of that squared is equal to 1. Hopefully you can kind of recognize this. What shape graph does this parametric equation have? The shape of this parametric equation is going to be an ellipse, and I'm going to rewrite it a little bit. That's going to become y minus 1 squared over 4 equal to 1. So it is an ellipse, so let's remind ourselves of just some conic section stuff. This ellipse is going to be centered at 3, 1. So there's the center. We have those a and those b values, but again, those just kind of tell you how far up and down or left and right you go. The 1 under x tells you how far left and right you're going. The 1 under y tells you how far up and down you're going. And it's always the square root of that number. So for the x's, we're going left and right by 1. And then we're going up and down by 2. Last year, we called those the a and the b values. But we're going to go up by 2, down by 2, and then left by 1, and right by 1. So we do see that it is an ellipse. Remember, when we eliminate the parameter, we just know the shape of it. What we don't know is the orientation. So for the orientation, we do have kind of two options. It's either going around clockwise or counterclockwise, one or the other. This one I probably wouldn't do kind of analytically. I would probably just choose some values for t to plug in and just plot the points and see which way it's headed, because it's not going to switch in the middle. So I might have t, if I'm going from 0 to 2 pi, I might just plug in the first two easy t values I could, 0 and pi over 2, and just plug that in. So when t is 0, the x is 3 plus the sine of 0, so that's just going to be 3. And then the y is going to be 2 plus the cosine of 0. Cosine of 0 is 1, so that's going to be 1 plus 2, 3. So this is the starting point for that. And then at pi over 2, the sine of pi over 2 is 1, so that's going to be 3 plus 1 or 4. And then the cosine of pi over 2 is 0, so that's just going to be 1. So we have 4, 1. I can already see that motion. This one is going around clockwise. So how can we interpret this? This is an ellipse. It's an ellipse going around clockwise, and that's kind of the pre-calc version of what we're doing. Where we're headed with this, and you can kind of see why knowing what the graph looks like is helpful. We might ask to figure out, like, hey, when is there a horizontal tangent line? When is there a vertical tangent line? Or maybe, can I just write the tangent line when t is equal to pi over 4? We can talk about the concavity of it. And that's kind of what we're going to start looking at tomorrow and Wednesday. But having an understanding of these graphs and be able to like translate them into rectangular form, I think makes it easier because it gives you at least a visual. And to be completely honest, a lot of the calculus we'll do, we might just say like, hey, this is probably easier to do in rectangular form. Let's just go ahead and convert it and just do it in a form that's easier to deal with. But that's where I am going to go ahead and stop today's notes at. Homework, I know we only have about like 5 minutes left of class. But the homework is going to be homework number 1, clearly, parametrics from pre-calculus. I did go ahead and share all this with your OneNote without Teams, because Teams has just been acting weird recently when I try to assign homework through it. So it's already in your OneNote, so there won't really be an assignment for it in Teams. And that's what I want you to get done. Try to get that done today, just because it's going to make the calculus part go a little bit more smoothly. Other things you can be working on, you do have some extended office hours today, so I hope you make use of them. But like if your briefcase binder grade is not a 100, definitely go back and complete all the missing parts and get that done. That grade can always be a 100. It is one of your summatives. You can also, if you need to make up or recover any assessments, reach out to me during office hours to get that done. And then if you're, feeling really anxious and want to get ahead, you can always begin preparing for the AP exams, as we really are going to start getting in that mindset of reviewing a whole lot of stuff for that exam. So at this point, I'm going to go ahead and let you go. I will see you tomorrow. Feel free to hang back if you have any questions. But tomorrow we'll go ahead and start how we do calculus with these parametric functions. But I hope y'all have a good rest of the day. I see a yellow hand, but I don't have my list up. So go ahead if you have a question.
Yeah, can you go back?